All right, well, thank you everyone for coming and for sticking it out to the end of the Expo. I am really excited to be here today. I was originally going to give this talk myself, but since we planned on giving the talk, someone new joined our team who's actually now a better person to give the talk than me. So his name is Denver. You just met him right here. He's our director of machine learning. Denver comes recently from Magic Leap, where he worked on gesture. He was director of gesture there, and here he's director of machine learning. But before I hand it over to Denver, I'll tell you a little bit about Occipital. So Occipital is about 60 people. We have offices in Boulder, Colorado, San Francisco, and recently we actually added a team in Gainesville, Florida. One of the interesting things that we've done, even though we're a startup and not a huge company, is find other interesting like-minded startups in our space and have either mergers or acquisitions. So the Gainesville team was known formerly as Paracosm, and maybe some of you have heard of them. They do LiDAR mapping. We've also acquired a couple of other teams, and we've got people that have worked on some amazing projects in the past. So a little bit about us. You might have heard of our original product called Red Laser. It was a barcode scanner on the iPhone. Back when the iPhone couldn't do anything with the camera, all you could do was take pictures. We got in a lot of trouble for actually trying to do something other than take pictures. It led to barcode scanning, which we sold to eBay. But our passion wasn't barcodes, so we kept Occipital. We started working on more advanced things in the path of augmented reality. We ended up building a panorama capture app in the early days of the App Store, and we launched the structure sensor, which maybe you've heard of. It's a depth sensor for mobile devices. The structure sensor actually has more apps even than things you might have heard of, like Google Project Tango. And it's probably the most ubiquitous way to use world-facing depth on a mobile device today. We launched a headset for mixed reality developers, an app to capture interior spaces, and a new embeddable depth sensor called Structure Core. But today, it's not about Occipital, it's about the industry, it's about geometric vision and deep learning, and how do these things work together, or should they work together? At Occipital, we've been, for the last couple of years, working on what we call our perception engine, which is an engine that can take any kind of camera, whether it's one that we make or one that somebody else makes, and try to make sense of the world. Not just sixth-off pose, which we all know is very important for augmented reality and virtual reality, but actually scene understanding and doing more than just pose. And the last talk was a good example of how with deep learning, we can start to do some things with cheap, simple cameras that we simply couldn't do before. So without further ado, I'm going to hand over to Denver to really take it from here. Denver?
Thank you. It's working, all right. Yeah, so in the past 10 years, two superheroes have arisen from the depths of computer vision. Geometric 3D vision and deep perception, right? So in this talk, we're going to look at these two approaches, and we're going to talk about their strengths and weaknesses, and we're going to argue that now is a good time to look at hybrid approaches to combine these things. So our first hero, geometric 3D vision, this has been a real huge commercial success for computer vision, a workhorse. It's led to new sensors that can do dense depth. From those sensors, we can do dense reconstruction of spaces. And from those reconstructions, we can do large 3D maps of very large areas. Even without the dense depth, we can still do very robust tracking with sparse features in most environments. And when that tracking fails, we can do rapid relocalization in sub-second kind of times. So one of the weaknesses of this hero still lies in its inability to understand semantics. And this reflects itself in some fragility in rooms, for example, where there's not a lot of texture. It's hard for these algorithms to latch on to features to do tracking, for example. Okay, so the second big hero from computer vision, deep perception, has just swept across the scene in the past 4 years and done made stunning progress on all kinds of semantic understanding. Here you can see the progress it's made on the ImageNet image classification task. In 2015, that exceeded human accuracy with ResNet. In 2014, it exceeded human accuracy in face verification. 2016, it exceeded humans in speech recognition. And just recently, it's had really impressive results on 3D pose and 3D articulated pose estimation, as you just saw in the last talk, actually. And you can see, even in very cluttered scenes and dynamic environments, it can still do this with sort of arbitrary number of people in the scene. And as these techniques have evolved and matured, it's becoming evident that you can take a single model and give it multiple tasks, and it can do well on all those tasks simultaneously. And this is useful not just for efficiency. You can do one pass through a network and still solve all these problems simultaneously, but it actually helps in accuracy to have multiple tasks. Each task kind of informs the other one and improves the accuracy of the model to do this large joint inference problem. So it seems like we're heading to the point where in the not too distant future, we're going to have a single deep model that can have semantic understanding of the world as well or better than humans in all kinds of different ways. Still, semantics is not the whole story, and a lot of the most impressive work in deep learning has actually come from combining this semantic understanding with sort of more classical reinforcement learning. So in 2015, using this approach, DeepMind was able to build a program that could play Atari games better than humans, and of course in 2016, AlphaGo beat the world Go champion. So combining is also something that we should think about when dealing with deep perception. So the one sort of place that deep perception surprisingly hasn't steamrolled as fast as it has in other computer vision tasks is really the 3D geometric stuff. It really hasn't been able to supplant the accuracy and the robustness of 3D computer vision. So because of this sort of complementary nature of these two tasks, we're arguing we should be looking at hybrid approaches. So this can go two ways. You could think of 3D vision tasks, and you could ask yourself, well, if we added deep perception to those, how can we improve them, right? And so this is sort of the classical case, computer vision room of nightmares. If you try to do sparse tracking in a room like this, it's going to be very difficult, and it's not going to be very robust. And that's not to say that this room is devoid of features. It has features. It has corners. It has edges. It has lights, shadows. And humans can navigate in that room just fine. So we expect that if we can use a deep model to learn those features that are not traditionally useful for 3D computer vision, then we can augment 3D vision techniques pretty robustly. And we've seen this in the past few years. We've seen attempts at deep models doing room layout configuration and being able to latch onto these edges that are very subtle cues that don't have overt texture that you would expect from like a 3D vision. Okay. So we could go the other way, and we could say, okay, now what if our goal is semantic understanding, the sort of the domain of deep perception? How can 3D vision help that task? So one great example of that is just very recent work by Diane Neisner, where they consider the task of not just doing semantics in isolated images one by one, but in taking a fully reconstructed room and understanding semantics in that fully reconstructed room. So if you first start with a 3D reconstruction, and then you have knowledge of a camera pose, and you have your 2D images that you feed into a CNN, you can then aggregate the labels of those semantic features across the whole room. And you can, in principle, reduce the error by an order of magnitude compared to just looking at the images themselves one by one. And so there's another interesting way 3D vision can help deep perception. It relates to sort of the precision at which you can estimate scale. So if deep learning is good at doing what humans do, like semantic understanding, you might say that, well, with semantic understanding, I can get an idea of the scale of a room just by looking at the objects in the room and understanding the scale of those objects. Like I know what size a typical chair is and a table. So I could look at this scene and I could have a pretty good idea of scale just from semantic understanding. But still, if I were to ask you, is this thing 130 centimeters, or is it 140 or 150? Like, it would be hard-pressed even for a human with their advanced understanding of the scene to precisely identify the scale of those objects. And honestly, it's worse. There's a more fundamental problem here. There's actually infinite number of rooms that could have generated this single image. There's this ambiguity of scale that no semantic understanding alone will be able to resolve. You really need some kind of way some hard geometric evidence before you can really pin down any sort of scale in a room like this. So this is just one example, and sort of the general theme here is that deep learning excels at human-like understanding, but humans, they're not the best at everything. They can be fooled in various ways. And having this sort of very rigorous mathematical, geometric way of looking at the world, adding that precision, can really help with deep learning as well. All right, so one of the obstacles to doing these kind of hybrid approaches really has to do with the data itself, 3D itself, in fact. Deep learning has really been driven by these high-quality, large data sets that have been labeled semantically, and that's driven progress tremendously. Unfortunately, the data in 3D is much harder to collect. It requires specialized sensors, and the data is just not very clean. It has holes. It's not well structured. You can't just stack up a bunch of 256 by 256 images and feed them through a CNN, right? It's much less consumable by a typical deep model. And then finally, there's another dimension to this data. So it just geometrically scales the amount of data and therefore the amount of compute required to crunch through the data. Okay, but despite this, we're still arguing now's the time to do hybrid approaches. The data problem is getting better. In the past few years, we're seeing more and more data sets that have come from structure sensor type data sets and whole reconstructions of rooms and even larger spaces, whole buildings. And the academic community has risen up and provided semantic labels to these. So we're in pretty good shape now where we can start to hopefully drive some 3D model building with this data. Of course, Moore's law, and especially with regards to GPU performance, has continued. So the compute problem is going away. But even more importantly, there's been on the scene some new specialized ASICs that are designed for deep learning and 3D geometry that can be brought to bear on this problem and can make it power efficient, even with mobile devices, to crunch through these big models. And then finally, just the openness of the deep learning community. Whenever a new model achieves a new milestone, that model's like instantly available for people to try. And the new frameworks such as TensorFlow and PyTorch are sort of removing the dark art of deep learning and making this technology just more accessible to more people. All right, so we've argued it's a good time to do this combination. So what might we expect to see with these hybrid approaches? So here's just a couple examples. So from the AR, VR perspective, typically if you want to enjoy a VR experience, you have a room, you have to sort of prepare the room ahead of time. You move the furniture out of the way, instrument the room with a lighthouse. Wouldn't it be great if you could just put on your headset and just scan the room a little bit, explore it a little bit, take note of all the semantic objects in the room and the walls and the obstacles, and then go into VR immediately. And then as you explore the room, you get notified of whatever semantic objects happen to be in your way. Compare this to sort of a room setup procedure that you'd have to do today, where all you would get is sort of phantom walls. Here you can get phantom furniture based on whatever's in your room. And we could take this idea even further. If we had good semantic understanding of the objects in the room, we can incorporate those objects into the VR experience. You could sit in the Iron Throne instead of your chair. And we can even handle dynamic objects, people and pets as they enter the scene. They could be present in the VR space as well. And we could even get fancy and we could incorporate them directly into the experience so they don't break the illusion. So I don't know if anyone has saw our demo upstairs. This is just the beginnings of this idea of this automated configuration for VR. And on the left, you see here's someone just scanning the space, and just for the first time, he's building up a map, building up sort of a set of lines and walls and a ground plane. And this is all completely 3D computer vision, by the way. I don't think there's any machine learning in any of this at this point. But then once you've built that map, you can then go into your virtual world, and we can do automated collision detection, and just like we said, but we don't have semantics here. We just have, here's an obstacle of some sort, but the next step is to add machine learning to this and actually get semantics and allow this interaction to be richer. So looking forward even further into the future, we've seen arising in the past 4 years, these audio assistants, Alexa, Google Home, et cetera, been very useful for us, but they're very limited. They don't have eyes. They don't have any spatial understanding. You can't ask them, how many calories have I eaten today? You can't ask them how many gallons of paint would it take to paint this room. So obviously we could give them eyes, and they could help out a little bit. We could look at people, and they could tailor their responses to the individual people who are talking to them. But they're still kind of stuck in space, so they're still limited in what they could do. Really what you want to do is give them eyes and give them locomotion, some kind of robot wheels or even human legs to explore the space. And once you've done that, now you've opened up all the stuff we've been talking about in this talk. Now you can make use of the spatial computation, spatial semantics that this hybrid approach would enable. And you can now start to get to the mythical AI assistants and robot helpers that we've seen in sci-fi for the past 100 years. Okay, so anyone who wants to start developing this kind of stuff, Occipital has already some SDKs that are capable of doing a lot of what we're talking about here. The machine learning aspects of these are not in place yet, but they will be rolled out over time as we ramp up this machine learning effort. And you can visit developer.structure.io to get started. And that's it. Anyone out there who's a machine learning or computer vision engineer on the job market, we're actively hiring. So we'd love to hear from you. Questions?